So, all right, so let's do a quick recap. We were studying the D equals to 4 effective field theory for the Ising model, because that's the only case in which we can do some effective field theory business. And Ising model effective field theory we found to be this, which is a scalar field theory with a 5-4 interaction. Everything above was irrelevant. And we also discovered why this value mu0 square must be less than 0 when t less than tc to get ordered phase, meaning all spins up or all spins down, indicated by the average magnetization being a constant value other than 0. And we need this parameter to be greater than 0 when t is greater than 0, such that the average magnetization is 0, which is the disorder. And last time we asked the question, what happens actually? Why is this happening? Why is the phase transition happening? What's the mechanism that drives the phase transition? And we tried to get some qualitative argument using the domain walls, but failed partially. So I think I fixed the argument for good. Let's see if you guys agree. And let's recollect what domain walls are. Imagine we are in t less than tc setting, then this parameter is negative, meaning this potential has two minima, right? So when t is less than tc, u of phi, which is just this part, as a function of phi, had two minima, each of which was m0 and minus m0. And the domain wall solution is basically, it's not quite a solution in the sense that it's not the minimum action configuration. The minimum action configuration we last time found to be just everything to be plus, or everything to be in this minima, or everything to be in that minima. But this is something that we are trying. Let's imagine that at the boundaries the spins are all, or the field phi goes to minus m0, but there is a region in the middle where the field goes to m0, with the transition happening along this yellow line all around the surface. So along this yellow line, this is the profile of phi. If you go with position along yellow line, this is the profile, like a tan hyperbolic, with the change happening in, roughly speaking, a width w. Last time we also computed how much this width should be. I cannot remember exactly, so let me just look it up. Right, so the width was like square root of 0 square, absolute value. So we want to know if this configuration is a possible configuration that we can have in the system. For that, we have to find what's the probability to have such a configuration. And the probability of, I'll just call it a wall, just like everything in StatMech, is just e to the minus action for the wall by partition function, the total partition function. So we want to find the action due to the wall. So action due to the wall is nothing but, we're going to estimate it just like before. So in most of the infinite volume V, the field is either plus or minus m0. And since this theory has the Z2 symmetry, meaning phi going to minus phi as a symmetry, be it plus m0 or minus m0 all over, the action is going to be the same. So apart from this boundary, right, the action is basically the same as having all spins the same, right? So let's just denote it to be some number times volume, right? To make things dimensionally easy, let's just normalize it with the cutoff in d dimensions, right? So this f is just a number now. Why do we expect it to be of this form? Because we are assuming thermodynamic limit, or we can just compute it, just plug in m0 here, and then this is 0. These are just numbers. This becomes the volume, right? Now, this is if all of the spins were all the same. But when we have a domain wall, we have something happening along the boundary, right? This is what's happening along the boundary. So the spin field phi is changing value from here to here as we go along the yellow line. Meaning this term is non-zero along the yellow line. We don't have to compute it exactly, so we can estimate it. So the phi field is changing from minus m0 to plus m0. So the change in delta phi, well, grad phi is like delta phi by delta x, that's along the yellow line, but times a, which is the area of the boundary line, and delta phi is nothing but it goes like m0, right? And the delta x is nothing but the width times a, that's delta phi. Now we need to compute, whoops, sorry, this is delta phi. Yeah, now let's compute d4x or ddx delta phi square, right? So that would be what? Square of this, m0 by w square times well, this change is only happening along this direction, right? So that dx integrated gives me a w. The rest of the d minus 1x gives me the area of this white line, right? Just to be consistent, let's do dimensional analysis and just pull out a factor like this. So recall that mu0 had dimensions, right? We can quickly remember this to be like the mass term in quantum field theory. So in the length dimensions, this has 1 over length square dimensions, right? And this whole action is written in mind with a cutoff. So in the position space, the cutoff is just the lattice spacing, which we take to be, let's say, epsilon. We already took it to be epsilon, whatever that is. So mu0 square at the cutoff is naturally written like this, with k being a real number, and k is the function of time, temperature, right? And what else we need? So m0 is nothing but the phi. We can either plug in the dimensions of mu0 square and lambda 0, or remember 2 lectures before where we found the dimensions of phi in such a way that this first term is dimensionless, right? So we found m0 was like a length to the 2 minus d by 2, right? Dimensions of m. So is that right? I think that's right. Right, so we can use this and this to write this bit. Last week we called it the string tension. This is the extra energy contribution due to the wall. We called it to be sigma, the string tension. Just do dimensional analysis and we find it to be some sigma tilde, function of temperature, because W and M are all functions of mu0, which is a function of temperature, divided by epsilon to the d minus 1. You want me to work it out? It's pretty simple.
We trust.
Yeah. I mean, it has to work out, right? And sigma tilde is just a real number, right? So overall, we have fv by epsilon d plus sigma tilde t by epsilon d minus 1 a. That's the estimate for the action for having one wall, right? Right. So there is something that we missed out on this formula. If we can have this wall, the same wall with the same surface area in many different ways, we have to multiply with the multiplicity, right? And that's what we want to find next. So the multiplicity, this is where the exponential problem comes in, is how many ways can I draw a wall with surface area A, right? Only then I have the same action, because this bit is going to be the same, roughly speaking. And if A is fixed, then no matter how I draw it, it would have the same S wall, right? You would have many configurations. So we want to find out how many ways can you draw a curve like that. So yeah, so number of ways to have a surface of area A goes like so. Last time we looked at a simple case of 2D surface area, which means perimeter, right? So for that, as George correctly pointed out, we should divide space into boxes of size epsilon. Then the question is, given a length L, how many ways can you draw a closed curve with length L? And I don't have a proof, but from what Siddhant was talking, I feel like this is an exponential problem. So the number of ways is nothing but e to the alpha times length in this case, but in general A. But as Gary told us last week, this must be like this, with alpha being a number of order 1, right? So probability of having a wall is multiplicity times e to the minus s wall divided by z, which is e to the minus f e by epsilon to the d minus sigma tilde of t minus alpha a epsilon to the d minus 1 by c. So the last week's hunch was correct, right? So if we find probability of having a wall divided by probability of having no wall. So no wall is just this. So we would have z's cancelling, this bit cancelling, we would get e to the minus sigma tilde t minus alpha a by epsilon d minus 1. Now when t is less than tc, then we can see the string tension is proportional to m0, so it will be generically some large number compared to alpha, which is of order 1. So this factor is larger than this factor, so it's e to the minus positive number times area, which is suppressed. Right. So when t is less than tc, right, m0 is typically large. I mean large compared to 1. I can just go below tc enough such that this is mu 0 square when like t minus tc, right? So if t is significantly below tc, then this is a negative number, which is big enough, so you can imagine that this is bigger than alpha, which is typically of order 1. So it must be that when t is below tc, significantly below tc, this factor is larger than this factor, so this is e to the minus positive factor times area, which is suppressed compared to which is less than 1, right? So probability of having a wall is less than probability of having no wall, so you wouldn't have any domain walls. However, when t goes to tc, m0 vanishes, right? T goes to tc, mu0 vanishes, so m0 vanishes. So this thing goes really small, meaning this term dominates, so it's minus minus plus e to the plus alpha by d minus 1. So probability of having a wall becomes larger than probability of having no wall as we approach the critical temperature. So at the critical temperature, such domain walls can arbitrarily form, meaning I will have a wall here, wall at random places, then I lose the order, meaning all being plus is lost because I can just put random walls at random places, so it basically looks disordered. So as we increase t from below tc to above tc, domain walls proliferate, destroying order to disorder. That's the mechanism. Is that concrete? No, just all of it is just minus. Imagine this middle blob is shrunken to 0. And if it's all 0, then this is the only, so S no wall is, and there is only one way, there is no multiplicity. So all the dimensional issues are fixed, I suppose. What do you guys think? Mm-hmm. Yeah. Yeah, I don't know. I just made that up. Yeah. Yeah. Why should alpha be order 1? That's something you should tell us. Yeah. It's not blowing up. It's just, yeah. It's not large. It's just large. I just want to be larger than alpha, which is of order 1. Yeah, we already concluded that there is ordered phase. Um, Roughly speaking, we also need to have this argument to conclude that ordered phase, because we have to make sure that this wall configurations do not appear. And that relies on this argument, I suppose. Yeah, but how do I don't know what alpha is. So maybe we have to do it upside down, like in experiments we have ordered phase. So this must be true. Alpha must be in such a way that, yeah. Or there is probably a clever way to say that alpha is less than this when you are below TC, which I don't know of. Yeah, it's consistent with each other, but which follows from which is slightly circular, I feel. Yeah. Partly the reason could be that I dreamt of this argument. This is not something that I found on any textbook. There is an analogous argument that's always presented for another phase transition. And I thought, oh, why do we not have this argument for Ising? And even this, this is my imagination. Uh, I guessed that it must be this form to get this. I don't know how to start from here and show this. It sounds reasonable, but I'm not sure how to do it. Yeah, that's why the argument last week was very mangled, because it was partial thoughts. I didn't fully these dimensions. So we are working with 4 dimensions, but this works for all d greater than 1. Yeah, maybe there's a way to find the d equal to 1 special case. So in d equal to 1 Ising model, there are no phases. Right. So the domain wall would correspond to points, and points as boundary surface area A equal to 0. So so this thing is just 1. Having a wall is equally probable to having no walls, meaning you can arbitrarily have walls. So even if you have ordered space, you can just add walls to make it disordered. So yeah, that argument is given in books for d equal to 1. But there is another issue, right? So d equal to 1, this is not the effective field theory. You would have to add many terms. So slightly again fishy. Right. All right. If that sounds reasonable, let's move on to critical exponents. Actually, computing stuff. It's been some time. So this be here. Get rid of this. Let's again recollect from this that we estimated based on the second and third steps of RG, which was rescaling the position units. Okay, let's recap the steps of RG. We take this theory, which has a cutoff, which we use to be epsilon, or we can also think of a momentum cutoff. K must be less than lambda, goes like 1 by epsilon. And the phi in Fourier space makes sense only when is equal to 0 when k is greater than lambda. Right, that's the way we impose the cutoff. And in RG, Wilsonian RG, what we did was take this action, integrate out right field phi as a phi plus mode, as a phi minus mode, where this has support below lambda by zeta, with zeta greater than 1, and this has support in lambda by zeta to lambda k, right? So these are the high momentum modes. Do we recall all of this? Yeah. If we want to probe the theory at some energy scale E, which is very small compared to lambda or lambda by zeta, then these modes are just not important. So we can just integrate it out. Integrating it out will give us a new effective action with cutoff lambda by zeta, and the effective action must have the same form as this, plus infinitely many terms, if you remember, because we have exhausted all terms that's consistent with symmetry. And then by now that new effective action has a cutoff lambda by zeta. To compare that effective action with this effective action, we change the units of the space variable x and the phi variable, and found that, oh, that gives us a relation of how these couplings evolve as we change zeta, meaning as we throw out more and more degrees of freedom. And from the second and third steps, which is the rescaling of fields and position variables, we figured out that the mu coupling changes like zeta square, mu zero square. This was a naive thing, right? Of course, we had to do this. This is the first step of RG. This is the second and third steps of RG, if you remember. So we didn't do this part yet. And we also saw lambda of zeta is lambda 0. It didn't change. So we called this relevant because as we increase zeta, this becomes larger and larger and larger. And this we call marginal because as we increase zeta, nothing happens naively, right? And the zeta square is the same as the dimensional analysis 1 by length square. Right. All the other couplings that we discussed, anything above phi 4 was irrelevant, meaning it goes to 0 as we increase zeta, meaning at long distances that terms are just irrelevant in the colloquial sense. Now, I also mentioned that when we include interactions, when we actually do the first step of RG, meaning this integrating out degrees of fields, these relations, these naive relations are supposed to change, right? So we already know that this is a relevant thing. So that's probably not going to change. Well, it will not change. But what about this? Is this going to be relevant or irrelevant due to the first step in RG? That's what we want to find now. Is the idea clear? Right, so step 1 was integral d phi plus. Just trace over the high energy modes. Second step is x rescale to x prime equal to x by zeta. Change units so that the cutoff of the new effective theory matches with the cutoff of the old theory. And the third step was change the phi minus to some phi tilde, which is equal to something which I don't remember, such that the kinetic term in the new effective action is just 1 by 2, no constants. Do we recall this roughly? Right. Now, well, we just didn't do this step. And from these two steps alone, well, actually this step alone, we figured out that this is relevant, but this is marginal, meaning naively marginal. We only did this step. But we have to do this and this step to figure out what actually is the fate of this coupling as we increase zeta. Is it going to decrease in the infrared and become irrelevant, or is it going to increase and become relevant? Right? We are going to find that now. So this is going to be the standard QFT thing that we have done in the past with slight modifications. So let's just act out this, right? If I separate the fields into phi plus and phi minus, I just plug it in here, right? So the original action, I can decompose it into 3 different parts. Well, up to my convenience, one of them is going to be just the plus fields. One of them is just going to be the minus fields. And one of them is going to be the mix of plus and minus fields, right? I'm going to do a slight rearrangement in between and include in the plus fields, I'm going to only include the quadratic term. And the rest of the phi plus things I will include in S interaction. I'll just write that down. So S plus 0 is going to be, I'm also going to Fourier transform this into momentum space, is nothing but by d that okay? Plug this to the quadratic terms, pick out the plus only bits, right? And Fourier transform. And let's remember that the cutoff in this, right, the integral is only non-zero in this region. The half, oh yes, there is a half. That's okay, right? And the integration region is, of course, because of this. It's non-zero only in this region. Now let's write down S minus. So S minus is just only minus fields, but everywhere, right? This is just convenience. I'm just shuffling it in that way. So that would be ddk by 2 pi d. There's going to be something identical to this, right? Half phi minus k that's from this. There's going to be something from here, right? Which is just trivial plus, well, plus lambda 0 by 4 factorial integral d4x phi minus x to the 4, right? There is nothing else with only phi minus. But in momentum space, well, we can do the Fourier transform and find it. This is an integral over 4 momenta, 2 pi d delta d sum over I 1 to 4 ki phi minus k1 phi minus k2 k phi. Just Fourier transform. This is nothing but d dx phi minus of x to the power 4. Fourier transform each phi minus, then we must get this. Right? The same reason why this is k and this is minus k. Right? You have two phis, so you have integral k1 and k2, but a delta function that imposes k1 plus k2 is 0. Right? Because when you do the dx integral, that's what you get. And in this case, you have integral k1, k2, k3, k4, e to the ik1x, ik2x, ik3x, ik4x. Do an integral over x, which is delta function. All the k integrals are left. Is that clear? I hope that's clear. All right. Delta what? Delta d of this summation of momentum. When you integrate that factor of 2 pi, you get 2 pi to the power 1 or 2 pi to the power 2d. This factor, is that what you're asking about? Oh yeah. So it's just this. It's convention, I think. Just convention of Fourier transform. In the inverse Fourier transform, you have ddk by 2 pi d, right? So that cancels this to give us 1. Right. All right. Now S int is the most interesting part. S int. S int is basically everything that we didn't write. So from the first term, we would have a phi minus k, k square plus mu square, phi plus k, right? But that's 0. Exactly. One of them is 0 in this region, the other one is, sorry, one of them is non-zero in this region, the other one is non-zero in this region. So when you multiply them, the delta function can never be satisfied, so it's always 0. And then what's left is all coming from here. Let me remember what all terms I included. Okay, I'm going to be schematic because I don't want to write, k1, k2, k3, k4 for factorial integral k1, k2, k3, k4, 2 pi to the d delta d sum I 1 to 4 I. Okay, running out of board space. Times. You would have a phi plus power 4, just like phi minus power 4, right? Just imagine that it's phi plus k1, phi plus k2, blah, 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 blah. And then we would have 4 times phi plus cube phi minus. Why is it 4? Because all the k1s, k1, k2, k3, k4 are identical, so all combinations can be lumped into just one term. Is that okay? And then 6 phi plus square phi minus square, this is just binomial coefficients, plus 4 phi plus phi minus cube, and there should have been a 1 phi minus to the 4, but I already put it here. Is that okay? Right. Okay, so erase this. So the first step of our G, integrate out d plus, phi plus. So we will do integral d phi plus of e to the minus s, right? And we defined the result to be e to the minus s tilde, right? That was a new effective action. But now let's just plug this thing in, right? So we have e to the minus s minus doesn't take part in this integration. Integral d phi plus to the minus s plus 0 to the minus s int, right? And there was a reason to pick this to be the quadratic nice free action, right? Because do you recognize what this is? Yeah, what you would get from here is the free propagator. But what's this full thing? Kind of. Well, I'll just write it down. So this s minus is only a function of phi minus, right? And this is nothing but the expectation value of s interaction phi plus phi minus with respect to a free plus Gaussian field. So let's recall what the expectation values are. Just a path integral definition of expectation value. So this gives us an immediate advantage because what are we supposed to find? We want to find s tilde as a function of phi minus, right? Well, we can just take a log that gives us s tilde as a function of phi minus is s minus phi minus. So part of it we already found, right? It's just s minus minus log of expectation value of minus s int, right? Now we make a non-harmful assumption that assume lambda 0 is such that lambda 0 is small. Oh my god, somebody's bombarding me with emails. If I take lambda 0 to be small, right? Why can we take it? Imagine that after all this business, lambda 0 turns out to be irrelevant, right? Then we can just go to large values of zeta where lambda 0 is small, and in that regime this assumption is justified. Now imagine if lambda 0 is relevant, then we can go to small values of zeta. Then lambda 0 will again be decreasing, and this will be justified, right? Yeah, but close to 1. Yeah, we just imagine, having a very large cutoff. Then the idea is if lambda 0 turns out to be relevant, then in the UV lambda 0 is small. So we go to UV and do this analysis. If it's irrelevant, we go to IR and do the analysis. If it's marginal, then it's order 1 already, and we assume perturbation theory is valid. So this assumption is harmless because we can justify it a posteriori. Once we are done with this analysis, we can say in which regime of parameter lambda 0 or in which regime of values of zeta this analysis is valid. So there will be a region in which this analysis is quantitatively valid, and the rest of the region we will just extrapolate the result qualitatively, which we will do next week most likely. So I'm going to just assume this for now. Well, we only know how to do perturbation theory, right? So S int is linear in lambda, so I can expand this. So let's do that. Then log of expectation value e to the minus s int with respect to the plus Gaussian field is log of 1 minus s int plus s square int by 2 factorial plus dot dot dot, and log of 1 plus stuff is stuff, right? So this is equal to plus minus s int plus 1 by 2 factorial s square int plus, right? Let's just recall what this is. Right? For small x. So what I've written down is just x equal to this plus this, right? But at s square order, there is one more contribution coming from here, which is minus 1 by 2 s int square plus, right? Just delete this and put a square bracket here, plus dot dot dot. Is this familiar to people? Yeah, this is the variance. And is it, well, I don't know how to prove it in general, that it turns out that, this is a variance which is the second cumulant in the statistical system. This is the first cumulant. In general, we will end up with the nth cumulant. Cumulant means just, all the, these things are subtracted off. So all the previous order stuff squared or previous order stuff multiplied to each other stuff is subtracted off. That's what it means. When we do Feynman diagrams, this will end up corresponding to connected Feynman diagrams. And this is called the cumulant expansion. Or just take it from me that this is called a cumulant. A cumulant, just we'll see that it means all the disconnected Feynman diagrams will be cancelled. So that's going to be in general true. And I don't know how to prove it exactly though. So this will end up being equal to 1 to infinity minus 1 to the n by n factorial s to the n int plus comma cumulant. And what this would mean is find this, then take off all the lower order things with correct coefficients. And this has a general enough definition, but I didn't care enough to look up what it is because we will not compute anything beyond this. Right, so how much longer do I have? 15 minutes? Right. Okay, so I have some more time. So yeah. So what this cumulant expansion thing gives us is the machinery of Feynman diagrams. So notice that this expectation values with respect to the plus field, but S int, as we see, have plus and minus mix, but the minus will never take part in this expectation value, right? So we can just think of, we'll see it explicitly, we'll think of phi minus as being external lines to Feynman diagrams, and phi pluses are always integrated over, so they will always be internal lines to Feynman diagrams. And then Feynman diagrams will give us a simple way to organize this perturbative series as usual. So let's just compute it and see if things emerge.
S minus also has lambda 0 in it.
S minus has lambda 0 in it, but S minus is already here. We have already found that part of the new effective action. So if you remember, when we found that mu goes like zeta square mu 0 square, what we did was completely ignore this part. We took S tilde to be just S minus, right? And then just enact step 2 and 3 of RG, then you would get that naive scaling relation. What this does is, right, S minus have like a mu 0 square phi square term, for example. What that extra contribution can give is a new phi square term, which will be there because there is a phi minus square times this thing. This is going to be integrated over. So you will get an extra contribution to mu 0 square, which is the delta mu. And now let's also think about, phi minus to the 4 term. From S int, it seems like you will never get the phi minus to the 4 term at a lambda 0 order, right? But if I take a square of S int, then I will have, the same thing squared, for example. We'll have a phi minus 4 times some new thing. So that will edit lambda 0 in S minus here, meaning S tilde will have a new lambda 0, new phi 4 coupling, which is essentially what we are trying to find. Right, so let's do order by order. Order lambda 0, meaning we are looking to find this, right? So S int has many terms. This term, for example, is just phi pluses, right? So under the d phi plus integral, this term will give me a number. It might be an infinite number, but it's not going to be an infinite number. Why? Because phi plus only has this restricted region, nothing is going to infinity, all integrals are finite. So this integral will just give me a number, but in the effective action, the numbers don't matter. So this term, I'm not going to look at it. Is that okay?
Which one you're not looking at?
This one. Because it's not going to contribute to the phi minus effective action, right? It's just a number under the d phi plus integral.
So it's like a overall normalization.
It's an overall constant that I can add to the S tilde, which doesn't matter, right? Now, what about this term? Okay, let's look at this term first. This term under expectation value is 0. Why? Because we cleverly chose the phi plus free action to be quadratic. So since this is 0, this term is going to contribute 0. Do you see why this is 0? Is there a confusion? So what is this? This is like d phi plus e to the minus s plus 0 phi plus. Quadratic, so it's e odd in phi plus, so this must be 0. By the same argument is 0. So this term is also non-contributing. We only have this term, which we will now compute. So let's find S int plus. What's that? Let's just take everything in. We have 1, 2, 3, 4, 2 pi d delta d sum ki lambda 0 by 4 factorial, then 6 times phi minus square. Let's put in values now. Phi minus k1, phi minus k2, which it was originally analogous to this, times phi plus k3, phi plus k4 plus, right? Is that clear? You seem confused.
Yes. thinking about, you know, how they calculate the expectation value.
I
What's
see.
the right expression?
What's the expectation value for this? I was hoping that you guys would know. You know, put another 5 plus here.
Right.
That's just a propagator, right?
Yeah, yeah.
We want to compute it. I can compute it very quickly.
Yeah. Can you write it out?
Yes. So the idea is you first compute this. Since it's a Gaussian, right? You can do Gaussian integrals, and recalling that something like that, right? Which we can write as b, right? So this is going to be e to the integral x y j x d inverse meaning this thing inverse, or in momentum space, integral k j k 1 by k square plus mu 0 square j minus k, right? And to get two 5 pluses out, you differentiate twice with j and set j equal to 0 after, which brings down this thing.
Right. Yeah, that's yeah, I get that.
Yeah, I can even make it more transparent, maybe. K1.
So for some reason, I'm just struggling to understand where there's no exponent in the expectation value s int plus.
Sorry, what?
There's no exponent in the expectation value s int plus. Like rather the exponential is in the angle brackets on 5 plus k3.
Can you say that again?
Yeah, so right, so this expectation value s int plus,
Uh-huh.
it's just this, and then the 6, and then 5 plus, 5 minus.
Yeah. So it's only coming from this term, right?
Right, so those are not squared, right?
These are squares.
Right? They're squared here then?
Yeah.
Right?
So it is squared.
Squared, oh, damn it, that's right.
It is also squared.
Right. And then
So
these
remember,
are-
this was my shorthand to not write this out.
Right.
So import all of this there, import this, but we just remember that product of phi's is at all at different k points.
Right. Okay. Oh, okay. 5 plus just gets taken down from the functional derivatives. So that's how you end up with the angle brackets there. Is that right?
No, the angle brackets is on the left side already.
In the integral, actually.
In the integral?
So yeah, angle brackets 5 plus, 5 plus.
Right. So you
That's
just imagine putting an angle bracket here.
Yeah.
And that angle bracket only affects this guy because it's with respect to the plus.
Right.
Everything else is just random things that multiplies it.
Right. Right. Okay. Yeah, that makes sense.
Yeah. So this thing we already know. This is given by 1 by k square 3 plus. And this momenta has to be equal and opposite. 2 by the That's clear. The equal and opposite again is coming from some sort of translational invariance. There is a delta function outside. Yes.
The only configuration possible is that phi minus has equal and opposite momentum and phi.
Correct. So I'm going to make it into a picture. Let's imagine not having the curly brackets, sorry, angular brackets. Then let's draw phi minus with a solid line. So there are two phi minus and there are two phi pluses, which I will draw by dotted lines. So this is phi minus, phi minus, phi plus, phi plus, with momenta, let me just call it 1, 2, 3, and 4. But what the angular bracket on phi pluses does is connect these two. Oh, but okay. So this vertex has the property that it conserves momentum. So here we have 2 pi d delta d k1 plus k2 plus k3 plus k4. And the angular bracket, or taking the expectation value, just connects this line with this line and makes it a propagator, such that this outgoing momentum is equal to minus that outgoing momentum coming from here, right? So taking the expectation value with plus makes it with 1, 2, right? So that's just pictorial, but we can just plug this in here and see what we get, right? So s int plus is 24 by 6 is what? 4. So lambda 0 by 4 integral. So k1 and k2 integral are going to stay. K3 and k4 integral, I can do one of them, right? And the sum over delta function k1 plus k2 plus k3 plus k4 just becomes k1 plus k2, because k3 plus k4 is 0, right? So we are left with k1 k2 integral 2 pi to the d delta d k1 plus k2 phi minus k1 phi minus k2. Well, I can do this integral too, right? And just write it as a single k integral. Kill this. Let me just write it as d dk 2 pi d phi minus k phi minus k, and then the 3-4 integral. One of the integrals is done. Another integral is left with this guy inside. Integral d dq 2 pi d 1 by q square plus 0 square. And recall that this integral is from lambda by zeta to lambda. Why is that? Because this expectation value precisely does that, right? There is a theta function that's sitting here too, that restricts momenta to this range. Why? Because the free action S plus was restricted to be in this region, right? And what's the range of this? Right, 0 to lambda by zeta, just because these guys have only support in that region, right? let me just call this some ID zeta, some integral in d dimensions, and it's a function of zeta, right? So let's figure out. Okay, I can just figure out. So in S tilde, right? S tilde will have what? Will have integral ddk 2 pi d 0 to lambda by zeta phi minus k phi minus k times um, um, mu 0 square, that's coming from this, already had that term, and now minus of this guy, which has what, um, um, minus lambda 0 by 4 id zeta. Is that clear? Just plug this in. Minus is coming from no minus maybe. Yeah, minus minus cancel, so no minus. Yeah. So there is a minus here. There is a minus here. That's what's happening. Right. Now that's first step of RG done. The second and third steps are very easy. Just rescale the k. So we'll end up mu square zeta, same as before, but mu 0 square plus lambda 0 by 4 id zeta. Now let's imagine what happens. Lambda of zeta. There is no quartic in phi minus term, right? So lambda of zeta at order lambda 0 do not get any corrections. So it looks like zeta to 4 minus d lambda 0. Is that okay? Yeah. So let me make one final point, and then we can disengage. So remember we said mu 0 square was the relevant parameter that must be tuned to 0 if we want to hit the critical point, right? That's what we argued in the, well, I erased it, the initial action. To hit the critical point, we must have no length scales, and the parameter that's relevant is dimension full, so it must go to 0 to hit the critical point. So we tuned the t to tc, and mu 0 squared just becomes 0, and we hit the critical point. Lambda 0 could be anything because it was marginal. But after doing RG to first order, what we find is this. Imagine mu 0 square was 0, right? But RG generates a new master. See what's going on? So if I draw a picture, if I draw this to be mu square and this to be lambda. Previously what we said is we just tune temperature such that mu vanishes. Lambda could be anything. But after doing all steps of RG, what we figure out is that even if this is 0, but lambda is something else, after RG we will generate a flow like this. 1 over uh, 1 over what? Some power of 1 over z. Then what? No, this guy is there always. Um, yeah, but from dimensional analysis, we must conclude that these things have the same dimensions, and what you said wouldn't happen. Is dimensionless in 4 dimensions, right? So that picture was wrong. So if I start with some lambda but 0 mu after Rg, I will end up with some mu, right? So our physical picture was slightly wrong. When we tune T to Tc, we are not tuning mu 0 square to 0. We are actually tuning this linear combination to be 0. We must tune T to Tc to hit the critical point. But at the critical point, mu is 0. How can mu be 0? We must be tuning this linear combination in the bracket to 0. Right? So it's just slightly non-trivial, but you see what I'm saying. Roughly speaking, if we start here with 0 mu, then we end up at infinite mu after Rg, because even if we didn't have this, that generates a mu, but it goes to infinity when zeta goes to large. But if we want it to be 0, which we want at the critical point, this linear combination must be 0. This linear combination is a function of zeta, yes. Let me think about it. Yeah, I have to think about it a bit more carefully to say exactly what's going on. Yeah, but that was the case previously too. Maybe no, not true.
I guess it has to be some range of zeta where your lambda not assumptions. Can you figure that out right now?
Yeah, from this it's hard because lambda 0 is still marginal, right? We have to go do the second order. Yeah, so next week I think I will clarify this a bit further. Now I don't have it on top of my head. But the point is, the take home point is that at order lambda 0, there is still one relevant direction, right, in this space of couplings. It's not naively this thing, it's some linear combination of this and this direction. That's the idea, I think. and this still remains marginal, right? It doesn't run. Yeah, so how exactly the flow looks is what I'm thinking now. So, yeah, maybe I should figure out, what this integral is, and then we can find, differential equation for how this changes under zeta, and then we can figure out the flow diagram here, which I intended to do after doing one loop extra, but that's next week, right? Yeah, we'll clarify it then. All right.